Good morning, everyone. Welcome to the GHF workshops on real world classification. This is the fourth workshop in the current iteration of GHF workshops on data science. The entire workshop calendar can be accessed on our community website. The link for the same is in the chat. We'll be interacting with you on our Discord server. So please join that. You can follow the QR code on the screen or the link in the chat. And there's a channel for classification over there where we'll be interacting with you. So put all your questions, doubts, and comments over there so we can have a good interaction. Our instructor for today is Professor Rahul Dave. Professor Rahul is a co-founder of Univ.ai. He was previously a lecturer at Harvard University. He was on the original team for Harvard's famous data science course, CS 109, and has taught many machine learning, statistics, and AI courses both at Harvard and multiple conferences and workshops. Professor Rahul is also an accomplished computational scientist with a very strong programming background and veteran cosmologist with work in solar system astronomy and large-scale astronomy, databases at ADS, which eventually took him in the direction of machine learning and AI. He's really passionate about teaching and a big believer in exposing big ideas early on to students. So without further ado, I'll let Professor um, take on the course.
Thank you, Surojit. And let me share my screen.
Yeah.
Oops. I'm dropping everything out here. So I just want to make sure that my screen can be easily seen over here. So just give me a second. And I'm going to share it. So I am sharing my entire screen. At this moment, you should be seeing some slides.
Yes, Professor.
Okay, good. So that's good news that you're actually seeing these slides. You should also, if I switch windows, see a browser.
Yeah.
Also with the slides on it, which was not my aim, but here is the GitHub repository.
Repository, yeah.
You see this? And I'm not sure if you see the iPad over here.
Yes, with the hello. Yeah.
With the hello on it. Okay, good. All three things can be seen. This is excellent. Okay, but let's start off then. So this workshop is usually run by Matangi, but I'm doing it today. And I hope you guys have some fun. And I think we'll all have a bit of fun with it. If you've been following along in the sequence of workshops, you have so far done one on Python. You've so far done one on pandas. You've so far done one on regression. And with each coming workshop, you have gotten a little bit further along in understanding sort of like the idea behind machine learning, right? And last time we did regression, showed you some of the API of scikit-learn that goes into regression. And we'll continue on that today. And we'll be talking about classification, which is the idea of, am I an apple or am I an orange, right? You look at something, maybe you have a picture of something, you want to figure out what that thing is. Or you have some information about something, and you want to figure out what that thing is. So for example, the data set we're going to look at today is one of people, and it has various aspects of people, like, you know, their salary, their age, and all of these kind of things, and wants to predict their credit score. Or maybe more precisely, actually, it doesn't want to predict the credit score because that would be a regression problem, right? You're trying to predict a score, but it's trying to say whether they are high risk or whether they are low risk, right? High risk being that, if I'm a bank, I don't want to lend these people money, right? That's the idea. Okay, so there are two parts to this workshop. One is a set of slides, which are accessible, if you like, in this PDF over here. And then the other is a notebook, which is accessible in this notebook out here. And probably your easiest way to follow along is to follow along on Colab, in which case just click on this Open in Colab button. And if you do that, you should have the notebook show up somewhere here. on Colab. So I'm just going to wait until everybody gets to that step and make sure that everybody is actually able to access things. And then I'll start off proper. So if you're having trouble, ping us in the, let's see, where is it? Let me reload. Our Discord here. Okay.
Yeah, in the data science series. Yeah.
Data science series, and you can see active threads is a classification workshop thread, and here we are. And I will put another hello in here. So if you're having any problems, please write to us in here, and so we can make sure that you are able to open this in Colab. Once again, the URLs themselves for this workshop is in the Colab. Did we put it down there? If not, we should. Yeah, no, I don't think we put it here as well. We might as well put it in here.
Yeah, I put it in the chat. I'll put it over there also, Professor.
Yeah, okay, thank you. Okay. Okay, so since there's nobody respond on the chat, I'm assuming that everybody's able to get to here. Okay. So the boundaries between the good and bad are always blurred. We want to do classification. We want to figure out if somebody's good, somebody's bad, if somebody's male, somebody's female, somebody's high risk, somebody's low risk. How are we going to do this? Right? That's what we want to do. So a basic construct, right? This is coming in from Python and this is coming in from Pandas, is that we have some kind of data frame, some kind of table. And this table has different features, like date is a feature, average temperature is a feature, previous day rain is a feature, humidity is a feature. And then we're asking the question whether we have any rain or whether we don't have rain over here. Okay. Now, this is a yes or a no kind of thing. It could be a yes, no, or a maybe kind of thing, right? Maybe it's going to be rain. But these are different categories. And so we're trying to predict these various categories here. A useful thing in all of these situations is to actually turn the question around and ask the following. What is the probability there's going to be rain? Is there an 80% chance there's going to be rain? Is there a 10% chance there's going to be rain? Is there a 30% chance? Is there a 40% chance there's going to be rain? And now you can make a classification. Maybe I'll say that if there is more than a 50% chance of rain, I'm going to say it's going to rain. So I'm going to then go and say for 24th November, which is not over here, I would put it as a yes, it's going to rain because there's more than a 50% chance of rain. Now, I don't know about you, but if there's more than a 30% chance of rain, I'm taking my umbrella with me. And so I might say, no, 50% is too, you're asking for too much certainty. And I say that at a 30% chance, I'm actually going to take my umbrella. So I'm going to say it's going to rain. So what threshold you choose in a probability to make a classification is a question of importance. But let's, for the simple situation, say that we're going to do 50% right now. And the idea behind that is that, well, if it's 50% or 51%, it's more likely that it's going to rain than it's not. And so that's a good way to make a classification. Okay, so far, two ideas. One is that you have a classification. Is it going to rain? Let's call that 1 or true. Not rain, 0. And then the second idea is that you can write this in terms of probabilities. Okay, so let's go a little bit further. Maybe it's not just 1 and 0. Maybe it's the level of rain that you're trying to classify. There's going to be a lot of rain. There's going to be a medium amount of rain. There's going to be very little rain. Now that's a different classification, right? Now you could even actually split up that probability space of rain into different amounts, but it's not just the probability space that you're trying to split up. You're also trying to say how much rain there is. There's going to be 2 centimeters of rain versus 1 centimeter of rain versus 0.1 centimeters of rain. So you'd have these different levels. And then you have different probabilities for those, and you come up with some way of dividing that space up. So what I'm trying to say is that you don't necessarily just have single, two-class classification problems, rain or no rain. You can have a multi-class classification problems. One of the most famous data sets is this data set called MNIST. It's a data set of handwritten numbers, and it's by the U.S. Postal Service. And it's a very interesting data set because the U.S. Postal Service wanted to look at the PIN codes or zip codes, and they wanted to use those zip codes to be able to automatically route letters by having a machine just look at the letter and say, oh, Rahul wrote 02144, which is actually my zip code, and said, let's actually route the letter to 02144 but with an automatic routing machine. But for that, you need to be able to automatically recognize these numbers. And now you know there are 10 different numbers, right? 0 through 9. So you got to recognize 10 different classes. So this way you can have a multi-class classification problem as well. Okay. So in this kind of a multi-class classification problem, you have different sets of kind of probabilities. You might have a probability of low rain, probability of medium rain, probability of high rain. And so you look at this 19th November, and it says the probability of a low amount of rain is 10%, the probability of a medium amount of rain is 70%, and the probability of a high amount of rain is 20%. And of course, this depends upon what you set as your thresholds for low, medium, and high, but it has now become a three-class classification problem. So this is what you are trying to predict. This is what you're going to use. Previous day's rain, average temperature, humidity, all of these kind of things. These things, as you know, are called features. This is called a target. And it's going to be a general structure in all these problems. So the example that we're going to look at over here is a credit card company wants to pre-approve its customers. It has many relevant details about these customers and should they approve or not. So is a person high risk or is a person low risk, right? So low risk would probably be a good label. High risk would be a kind of bad label. And you have these different kind of items that you want to try and predict over there. So we're going to go to the notebook now and start looking at some of this data. We're going to understand this data. And this is going to be the general sort of like procedure. And this is really important. What I want you to do is to look at this entire process. It doesn't matter what classification algorithm you're going to use to do this. You're always going to go through this particular process. You are going to look at the data. You're going to look at the target and see what the distribution of the target is. You're going to do some exploratory data analysis. You're going to think of features and make all kinds of stuff along with the feature, messing up of the features, combining them and doing all sorts of stuff. You're going to do a train test split for reasons that we'll come to in a little bit. You are going to do some kind of encoding of what are the categorical variables. Like, what are categorical variables? Things of different classes, right? So you might say gender is categorical, male, female, transgender. That's a categorical variable with three different what are called levels in it. But sometimes categorical levels can have lots of levels. So for example, a very famous problem is the Rossmann-Kagel sales prediction problem. And the store ID is a sort of fairly important variable in that prediction. There are 1,000 different stores. So that's a 1,000 level categorical feature. Then finally, after all of that, we are going to look at the model. Okay. Then we are going to investigate this model and see how it performed. And then we are finally going to try and explain the model. And this process is kind of like the data science process that we go through. And as you can see, the modeling is only a small part of it. The entire process is what's kind of important. And we're going to see this entire process today in the context of a classification problem. So this is the first time you've seen this. Last time when we did regression, right? It was more just about the modeling. Now we're going to zoom out a little bit. Okay. All right. Let's see. Do we stop here or do we? Yeah, we can stop here. Let me actually. Yeah, we'll stop here. Cindy, you want to take over and run the notebook?
Yes.
All right. I can. I'll hit the cells. You just tell me what to do.
Yeah, so here as we can see, we want to install some libraries here. where we will use them for exploratory data analysis. SweetWiz, it's pretty sweet. Actually, you'll see. And we install Sharp for interpretation of our model, and Unrar for decompressing our library data decompression.
So that's going to take a little bit of time. So I will run it. And you run it by clicking this little cell.
Yeah, you guys also please run it on your PC while we are doing it here.
Yeah. So if you already have Jupyter Lab installed, please run it in that. Or if you want to run it on Colab, you can run it on Colab. It's totally your choice. I think the simplest way maybe to just run it on Colab.
So if you have any doubts in what professor has explained, please feel free to ask in between.
Yes, I have one.
Go ahead.
It could be a little too soon because the explanation is yet to come, but still I'll put it across.
Go ahead.
When we are considering, for example, the climate data, there are
Mhm.
there are going to be so many uncertainties because climate by its very nature is unpredictable and uncertain. So how does this process arrive at some kind of a fixed determinant or an indicator? Like and add to it climate change, the factors of climate change, etc. Yes, please.
So general point about any machine learning model, right, is that you are making a kind of prediction over here. That prediction is not an absolute prediction, right? That prediction is made with some probability. So if I say this is rain or not on 24th November, as you saw over here, had 80% probability, you can imagine 10,000 universes in which you're making this prediction. It's only in 8,000 of the, roughly speaking, 8,000 of those 10,000 universes that it will actually rain. In 2,000, it won't. Your prediction will be wrong.
Okay.
So yes, that uncertainty absolutely is there. It's just kind of encoded in this probability to some degree or the other. Now, let me go to the second part of your question.
Yeah.
And I think it's a very good question, because what you're telling me is that there are two levels of uncertainty. Level one of uncertainty is that, okay, we don't have those many measuring stations and so on and so forth. So all these measurements we've taken, average temperature, humidity, are not particularly accurate. So it's not, you say 38% humidity, maybe like 35, maybe like 43, right? So we don't know these features with exactitude. That error is not taken into account over here, but it can be if you want, because you can actually construct different data sets which take this error into account. It's more expensive in terms of computation, but you can do it. And in fact, people who people who run weather models and weather prediction models and even weather prediction machine learning models will actually run tons and tons of these simulations. And then kind of give you a probabilistic an envelope of these simulations. Now, weather prediction, to answer your third question, which is about the whole climate change aspect of it, does not necessarily go into everyday weather predictions. Sometimes it does, sometimes it doesn't. But if you're trying to predict climate change itself, you also have the same sort of variables that you have to deal with, right? A very good example is how quickly ice is melting. You made some assumptions for how quickly ice is melting, and that's going to have some climate change prediction stuff. Well, if the ice melts faster, your predictions change. And so in any kind of modeling process, the features can always be uncertain. And you're absolutely right. You want to take that into account. And the way you typically tend to take that into account is you run the model again and again many times with these different features. So I would run at 24th November with a humidity of 39%, at 24th November with a humidity of 40%, because if I'm not sure about this 38%. And that's the way you do it. Because remember, you have to propagate that error all the way through in your prediction.
Okay. Can we say that the outcomes of our work are only indicative and suggestive?
They are, I think it depends, right? I mean, on how good your predictions are. Climate, as you put it, weather prediction is a fairly hard problem to solve. So yes, your predictions are not that good. So yes, I think you could say indicative. But a lot of machine learning problems, you can actually say better than indicative, right? But what you're giving is a kind of error bar on the problem. You're saying it's likely to be in this range, right? And that's the best you can do.
Okay. And last question regarding this. In the larger scheme of things, then how are decisions made when the outcome is a probabilistic outcome? How are decisions made, taking into consideration?
That's
Yeah.
so that's like maybe an entire semester
Oh,
subject
okay.
called decision theory. No, it's not easy. But there are heuristics by which you make decisions. So for example, that probability thing I was telling you about the rain, right? That for me, my threshold may be like a 30% probability of rain is enough to force me to take an umbrella. So that's how I made that decision. Let's say you had written a model to figure if you had cancer or not. I'm not waiting for 30% for cancer. You tell me I have a 5% chance of getting cancer, I'm going in for a biopsy.
Okay.
So there is a framework in which these decisions can be made, and it's usually called the expected value cost framework. But you learn that in a more sort of like detailed machine learning course, which incorporates decision theory. But
So
if
it's
you
going
want to
to
Google it, go Google for
yeah.
decision.
So it's going to be subjective. Yeah.
Yeah, it's going to be subjective, and there are ways to do it.
Okay.
Which may make it more objective. Um, but there are assumptions which go in there as well.
All right. All right. Thank you.
Yeah. Okay. Okay, Sindhu, should I go ahead to the next cell?
Yes. So we are using pandas here. So we are importing pandas and NumPy. And we are trying to unpack the data that is present on the GitHub.
Right. So this is all um, in our workshop, right? So we're just getting this data from there. And then you're unpacking it and looking at it.
So here we are forming a data frame using pd.read CSV. So we are trying to look at the data, like what is present, what are the columns, what are the values in the columns. So it looks like there are columns named income, age, experience, bureau score, married or not, house ownership, car ownership, if they have car or not, risk flag, is that person risky to give the loan, or is that person okay? Profession, city, state, and current job years. Okay, this is the data that we have in this table. Okay, so let us see what kind of data types are in each columns. So income is an integer, as you can see. Age will be a float, is a float. Experience is a float. Okay, float number. So bureau score is a float. Married is object. So we have married as single or married. So it is an object. It is in string form. House ownership is also an object here. Is it rented or owned? Uh, and car ownership is also an object here. Is it yes or a no? Does he have a car or not? Risk flag is an integer, and profession is an object. City is an object. They're all in string forms, which our model cannot interpret this in string form. So we will go forward and change them to, yeah, you will see what we do with them. So after looking at the data, let's see. So the here target variable is a risk flag. We want to categorize using all these features that we have seen. We want to categorize this into this person into, is he risky or is he not risky? So normally people are not risky. Like as you can see, a lot of people comes under not non-risk zero. Risk flag is zero for 236,000 people, but there are few people, 43K people out of the data that are risky. So as you can see, using value counts and normalizing, So we can see that 84% of the people are non-risky and 15% are risky. Yeah.
So here's a question for you guys. Suppose I come up with a model, and my model is nobody is risky. What's the performance of that model? What's the accuracy of that model? I'm saying nobody is risky. So everybody, in other words, is a zero.
It will be 100%, but the model will not work, great, because
Will it be biased?
it will be biased. Right.
So what is a model which says that everybody is not risky telling me? What is it telling me about these 43,000 people?
It's like imbalanced data.
Yes, that's a good point. It's imbalanced data. Yes, very imbalanced data. But it's going to misclassify these 43,000, right?
Yes.
So its accuracy is going to be?
Accuracy always
Percentage accuracy is going to be?
above 90. Why? Because it
Above 90, or is it going to be? I'm getting this
Around
0.80. Yeah, go ahead.
around 80%, I think.
Yeah, in fact, to be precise, it's going to be around 84%, right? Because these are the people you got wrong.
yes, 15%.
Yeah. So the reason I say this is because by doing nothing, by doing no work whatsoever, just saying that nobody is risky, you have come up with a classifier. It's not a machine learning model. It's just a classifier that you came up with, which is 85% accurate. Now consider an even worse situation, like consider credit card fraud. Credit card fraud rates are typically like 0.5%, 1%. So if you came up with a model which said there was no fraud, what would your accuracy be? It would be off the order of 99% or more, right?
Yes.
And you'd be forgiven for thinking that this is a very good model. It's 99% accurate, such a good model.
No.
You'd also be out of a job because your boss would kick you out. Because your whole job was to find fraud. So this is kind of an interesting point, right? A lot of these models in which you have this kind of, as you put it, imbalance, accuracy may not be the right thing to look at. This is why we're going to be talking about actually doing these kind of measurements and trying to figure out what metrics are the right metrics to evaluate models with. So it's very important to realize that the simplest metric may not be the right metric that you want to evaluate a model with respect to. Okay. So shall we go ahead, Sindhu?
Yes, yes. So here we can see there are like two kinds of data types that we have. One is numeric, which is in int and float, and one is object type, which is mostly in string type of columns. So here we are seeing what are all the string columns. So here we have profession. It was a string, if you remember, married, it was saying single or not. House ownership, yes, it was a string type. And car ownership, it was saying yes or no. City, of course, string. State, it is of course a string. So we are trying to like accumulate all the string columns here, and yeah, after that we missed somehow device. As you can see, device was also a string. So we added that device to here. So afterwards, we are going to read the numerical columns that we have. Professor, can you scroll down
Yeah.
to
So let me
numerical?
just run these
Okay.
and this. And I mean, out here, I just looked for the column with the name 0. So this file is a bit weird in which the columns are, and often you'll find that your data files are weird, but this at least gives you the list of the string columns.
Yeah. So there is a file like we already have files where we have what are the numerical columns we have. So it is in CSV form. We are downloading it. Uh, we have already done it, and we are reading it in pandas as a data frame, and we are looking at what it has in numerical column list. And we have income, yes. Age, yes. Experience, yes, it is integer, uh, like numeric one. Current job years, numeric. Current house years, numeric. Bureau score, numeric, yes. So we haven't missed anything here, so we are going forward, and we are printing now just to look at what variables are, column names are there in each list. We are printing them. So in string column names we have all these, and yes, it covers everything, and numerical column names we have everything. And then we are trying to see for each column what are the unique values that the column has. So, in state, yes, we have all the state names: Maharashtra, Telangana, Andhra. They are all okay, but some states, if you see Uttar Pradesh, it says some bracket 5. So, this kind of data abnormalities will be there, and we need to look at them, and we need to edit them. We'll edit them. You will see. So list of units, unique cities. See, look at Warangal. We need to change it. We will change it. Dairy. See, sometimes what happens is Warangal will also be present, and Warangal 11, 12, like another format will also be present. Then they will be counted as two different uh, cities. So if we don't want that, so we need to find a way to solve this problem. So if you scroll down, uh, this is how we are going to solve this problem. So we are going to make it lower case, and strip and replace. So this uh, R strip and L strip. So it will remove all the spaces and all those kind of stuff that was in the string. And yeah, so it replaces any kind of abnormalities with nothing. So all these things.
Yeah, in this regular expression, the caret means not. A to
Not.
Z means not either white space or A to Z, and one or more of them. So now it will get rid of all your like open bracket, 5, close bracket, and all of those kind of weird things.
Numbers. So we know that in city names we will have only letters, and we have already removed the capital letters. So if the string doesn't, if anything that is not small letter, we are going to remove it and replace with none. So that is what this expression means. After that, we are looking at city names, the changed city names. Now you can see everything is in small letters, and you can look at Warangal, it doesn't have any tail anymore. So if you scroll down, now we are again looking at our data frame T1. And here you can look at city, changed one, and state also. Yes, looks good. It looks like our data in our data frame also. We have applied all these. So yes, now we are going back to slides for more concepts.
Okay, let's see where we are on the slides. There we go.
Hello, sir.
Yeah, question? Go ahead.
Yeah. So, what is the necessary of changing the capital letters into small letters? Why it is necessary?
So it's the same thing, right? What Sindhu was saying, that, suppose I had a Warangal with a capital W, a Warangal with a small w, and a Warangal with a capital W and open bracket 5 close bracket. By doing this, right, by normalizing everything to one particular form, you are making sure that any of these repeats don't happen. So if there was a coding error, and this happens often, right? Like somebody is writing this data in, right? They put Warangal with a capital W, sometimes with a small w. Sometimes they even misspell it and make it Waran Lug or something of that sort, and you have to figure that part out. But in all of these situations, you're trying to normalize your data so that it actually is in the same form. And some of these are programmatically more easy to do than others. Make sense?
Yes, sir.
Okay. Okay. So this was kind of like the look at the data, understand the data, pay attention to the Y levels and the distribution that we were talking about. So we looked at the data, we paid attention to the Y levels and saw there was a slight class imbalance over here. And so our baseline accuracy is 84%. I mean, if you're thinking about accuracy as a metric, you're already 84% accurate. Okay, so now what we want to do is we want to do something called exploratory data analysis. But even before we do exploratory data analysis, we want to do some splits in the data. And this is a little bit of a subtle point, and not everybody does it this way. But let's talk about that a little bit. So exploratory data analysis, we're really trying to understand our data, what's going on in our data. You're going to see each and every column and see what kind of distribution that column has. That's called a univariate distribution because it's looking at one feature and seeing what's happening. Sometimes you want to see bivariate distributions, two columns together. Maybe two columns are extremely correlated with each other, and you want to see this. Then you want to see if there are abnormalities, right? So I have like all the data in a column is over here, and then one value is there. It's an outlier. How do I deal with that? That's what we want to do. And then we also want to look at these key tipping points or categorical values that determine outcomes. Sometimes the existence of one categorical value that, okay, maybe everybody from Warangal is high risk, right? So the city equal to Warangal may be a kind of like a tipping point, which says that something weird is happening with Warangal, that nobody is trustworthy out there. They never pay back their money or whatever. Sorry if there's anybody from Warangal out here. I'm just using it as an example in there. So but let's go back to the code because there are some subtleties about this that I want to make sure everybody gets. And these are really important subtleties. I have seen so many students after a full data science course, even at Harvard, get these subtleties wrong, that I want to make it a point to sort of point out these subtleties to you right at the very beginning. So let's talk about it. So we're going to talk here. Sindhu, do you want to go ahead with this train test split?
So what we are doing here is train test split. So why do we need train test? So we have a T1, the data frame that we all the data we have, and we need to train test split because we want to train the data on some of these data points, and we want to test our model on some of these data points. So we are doing this train test split from sklearn model selection. Here we are providing it the input as T1 of string column names plus numerical column names, means we are going to train our model on both the string type of columns and numeric type of columns, categorical and numeric. And risk flag is our y variable. So after that, test size we are saying 0.33%, 33% of my data I will put for the test. And we are putting random state because every time we run this, we want to see the same splitting happening. So that's what is uh, about train test split. So after that, we are going to get T1 train and T1 test splitted in this way. So when you look at T1 train, you can see that all the variables are here good, and we have T1 train. There is an index that 160401. So these are the indexes that are given by the data. Like it could be any number that they like when while collecting the data, it was labeled like this. So it is not making sense to us anymore. So we want to change that index, and it is a good practice to have an index that is we are familiar with. So we are going to reset the index of train and test. After that, we are going to reset index by using reset index, and we are dropping the index that is already present here. So yes, now if you look at the data, that part is now it's not present, and we have our index 0, 1, 2 only. Yes. So if you look at the shape, how much data we got in train, how much data we got in test data frames, it is around as we have splitted, it should be 33% in test and remaining will go to train. Yes. Um, so we are going to do exploratory data analysis using SweetWiz as we were discussing. So we are going to produce the sweet report. Please run this on your laptop also. It will take a little bit of time. So in between, you guys can now ask any questions that you have in code or in concept.
Okay, so it first went with every individual feature, making distributions of those. Now it's going pairwise. And now it's done. And so it says use show commands to display save. And one of the commands is to display in a notebook. So
I have a question.
Yeah, go ahead.
So why did we, split the columns to object type and integer type? And we are, not doing something like one hot encoding.
We'll
Will we
come to
do
that
that?
in a little bit.
Acha, okay.
You're getting a little bit ahead of it, ahead of us. Yeah.
Okay.
We're going to come to that.
But I have one question. Why
Yeah,
was there need to split, the object and the integer part of the data frame? Why did we do that? I mean,
that we will answer that one.
Okay.
Yeah, absolutely. We will answer that one.
Okay.
So we have passed our train set to the SweetWiz, and we have set that risk flag is our target variable. So it has analyzed everything for us nicely. So as you can see, 84% of people in train data are also non-risky. One is 16% is only risky. Okay, so that's what we can interpret from this diagram. After that, let's go look into the professions. So as you can see, politician is ranked very high risky. Yeah, so this data is just produced on a computer. It's not real data, so doesn't represent anything about these professions, but we can just use it. So you can also see the correlations of bureau score, current job years of this data. Yes. If you go to married and open that, so you can see that single people are more risky than married people. Uh, yes. It could be that married people are more responsible. It would show that if it was a real data. Yes. Uh, and we can scroll down. We can also see how much data, like how much people are there in rented houses and how much people are there in own houses. So here you can see like 91% of people are in rented, 5% are in own house. And risk flag. So what risk flag here 16% means is that of the 171K people we have in rented houses, 16% of them are uh, marked as risky. So as you can see, the line is representing the risk flag notation, and the bar graphs are just representing how many people are present in the each category. So you can see by just looking at it how the data is distributed, and of the categories we have, which one is like high risk, which one has low risk here. Like, yeah, here we can see rented is high risk than own. It could be because maybe own house people has more financial stability. Could be. Uh, so we can make some interpretations out of these things easily. So if you go down a little bit, yeah, this is very high granular data, and it's impossible to make any proper interpretation from this one. And as you can look at states, some states, like many people are sampled from Uttar Pradesh, Maharashtra, Andhra Pradesh here. And you can also see how the high risk variates. So here it says Karnataka people are more risky, but don't hold it on us, it's just a generated data. So it says Kerala people are less risky. Yes. So that's how it's going. And as you go down to experience, uh, experience, so you can see like you can see there are outliers in experience. So there is no people who have 100 and 120 years of experience here. You can easily identify if your data has an outlier, and you can remove it or treat it as you may wish to. So you can also see that the distribution, everyone is has experience around 0 to 15 years. Mostly some people have 20 years. So if you can see the categorical associations, if you can see numerical associations here, correlations, you can see that age is highly correlated with experience years, which is very you like intuitive, because with age your experience is also increasing. So that way you can also interpret like which two columns are correlated by looking at these analysis here, correlation analysis here. Yes. Yes. So yes, that's what it is. Thank you. Yeah.
So I have a question over here. I see that Kunal has a question as well, but let me ask my question first to you guys. Why do you think I did the train test split before I did the CDA? And I'll give you a hint.
Train the model.
For the privacy, so like on the test state.
Train
Say
the
that
model.
again?
In order to train the model using the trained data set and test it with unseen data set.
Aha, tested with unseen data set. But if I had done this correlation, right? So this is essentially giving you some kind of idea. Let's look at another one because it's kind of easier to see. If I'm going to make the point that like, okay, folks from Karnataka are more risky, folks from Punjab are more risky, folks from Kerala are less risky. And I make this statement after having seen all the data, the training set plus the test set. It is bad. And why is it bad?
Will take some noise of the model.
No, it's not a noise thing.
There will be a bias.
We have not included those observations in the during training process.
Exactly. We have not included those observations during training process, right? This is our training set and that's a test set. The moment you make a determination of some feature by looking at all the data, you are presupposing the answer on the test set already. And the moment you presuppose an answer on your test set, your machine learning model will look like it's better than it was because you're putting information about the prediction in. And so you never want to do that. This is what's called data leakage. And this is why you do your EDA on the training set. In fact, if you have a good data science boss, like for example, if you are doing a competition at Kaggle, if you're a good data science boss, they will not show you the test set. They will take a cupboard and they will put the test set into the cupboard and only show you the training set. So you are not even tempted to do the whole thing, to look at the whole thing. So never make that mistake. Don't do EDA on the entire set. Now, having said that, let me tell you the caveat to this. The caveat to this is something that does not happen in this data set, but I've seen it happen at other places. So suppose I have these states. And suppose just by mistake, I somehow split my set so that I had no Delhi in the training set and all the Delhi were in the test set. This should not happen because you should be splitting it so that these are equally represented everywhere. That's something you want to be a little bit careful about. And usually it's not much of a problem if there are enough samples for Delhi. If there are very few samples for Delhi, if you only looked at 5 people in Delhi, it becomes a problem. But it might happen that if you have lots and lots and lots of different things, like the cities, right? Our cities are tons of cities. That you might have one city just show up only in the test set. And now you want to make a prediction for this. And now you're in trouble because you didn't see the test set. So, in a lot of situations, it is okay to see the X from the test set, the features. But is it okay to see the Y? Anyone?
Yes.
Yes or no?
Both X and Y should be observed.
No, from the test set.
Test set.
Should you ever be seeing the Y from the test set?
No, sir.
No.
No, right? It's okay to see the X, but it is not okay to see the Y. Because the moment you see the Y from the test set, you have already presupposed the prediction. And then when you look at a graph like this, with this line drawn out here, if it has included the test set, and you're going to make some decisions about which features to use based upon that, then you are leaking data from the test set. And this is why I just did the very safe thing. I said, before I do the SweetWiz business over here, I'm going to do it only on the training set and not on the test set. Okay. So important, very important. Lots of people get this wrong. To be honest, even I got it wrong the first time I did it. But lots of people still, after a year of data science, get it wrong. So don't make that mistake. Okay. Sindhu, is it time to do the exercise?
Yes.
Oh. Okay. So do you want to take over?
Yeah. Guys, Surojit Can you please post that link?
Yeah, I'll do.
Yeah. So yes, please open this Google Doc, and as you can see, can you open it, Professor? Um, so here, please take 10 minutes. We'll take a break and look at the SweetWiz data that you have on your collab notebook and make your own insights. Like, what do you think you can interpret from the data? And what are the new features you can think of, like apart from the features that we have in the data, maybe education. So we don't have the education details in the data, or any other features that you want to collect from the people so you can make a better prediction, and what are the insights that you can get from the SweetWiz analysis.
And
Please,
you can edit it directly in here. So just write it directly in here.
yeah,
You know,
just
the good thing about Google Doc is that multiple people can write into the same document.
yes, write your name and your insights so we know who is writing it.
So 10 minutes, right?
Yes, yes.
Okay. I will be right back. Hey, nobody's writing anything. Come on, folks. I mean, if you don't want to leave your name on it, just do it anonymously. That's fine too.
So everyone, write your name, or you can keep it anonymous, but write either give some insight or some additional features that you may feel are important. And you can write your name if you want at the top, and then the insight, and then the features. So Kunal is writing some very interesting features. So please, everyone else also take a look at the data that we have and write your opinions and what you think can be a good uh, feature or insight. So everyone who is editing, please leave some space above whatever you are writing so that the person above can also write instead of overwriting your comments.
Two, 3 more minutes.
Yeah, Professor.
Yeah. Sindhu, do you want to run with what we have?
Yes, Professor. Yeah. Kunal had made some very interesting features, real estate or other wealth possessed. Yes, that could act as collateral. Yes, we could collect that data. The likeliness of borrowers to progress financially in their professions. Okay. So how their salary is changing throughout the profession. Yeah,
Yeah,
that.
suppose like we know data science is an upcoming field and they are going to have good remunerations. So if a borrower is a data scientist, then we can hope to have recovery for good recovery prospects.
Okay.
So good upward mobility is what you're saying, basically.
Yeah, yeah.
Yeah,
Mm-hmm.
that's a good one.
Yes. So most of the users are in rental houses. Yes, that's an insight. Good one. It is better to consider income plus profession. Ashwin, could you explain what you meant? So that the chance of risk flag should be less.
Ashwin?
Ashwin. Okay. So insights from someone, market analysis of a particular area for a consumer base and product. Market analysis of a particular area for a consumer base and product. Okay. So for a particular area, we can add more data. Like for if you pick Warangal, you can add more data about Warangal. That's what you meant. Professor, is that a good strategy to have market?
Yeah, I mean, I think, you know, if you're looking at what people are buying in Warangal and stuff like that, right, that may be a kind of an indication of riskiness. So, I mean, I've noticed because I used to work for Seva Bank in Ahmedabad, that one very sort of like good indicator of loan repayment risk was how much money a particular family might decide to spend on a marriage.
That seems.
So if you're looking at marriage market purchases and stuff like that, you could definitely, I mean, at least in my experience, I definitely see that there was much, much higher risk involved.
Mm-hmm.
And I found that in Ahmedabad, at least, it was pretty much segmented by community. Some communities had very high social pressure to spend a lot of money in marriages.
Right.
Do you mean to say that those who were spending more on things like marriages were less likely to repay them?
Yeah, and yes, because firstly, banks don't typically give loans for marriages.
Right.
And so they landed up taking a lot of money. So the way it worked is that they landed up taking a lot of money from, the sort of like informal money lenders. And informal money lenders typically have interest rates like 15%, 20%, that kind of stuff. And that would wipe these guys out, and they were very unlikely to, be able to pay everything. In fact, in some communities in Ahmedabad, like even funerals, you had to throw a huge party. So it was not unlikely for a person to spend 50,000 rupees to 1 lakh for a funeral. For the party for the funeral. I'm not talking about the funeral. So, think about it. If you're if you're a daily wage earner on like 300, 400 rupees, and you have to now spend 1 lakh for a funeral, your loan repayment chances have gotten very, very low.
Someone has mentioned market analysis of a particular area for a consumer base and product. I do not understand the link. Like by the face of it, it looks something for a.
No, but this is exactly what I'm saying. So if you know that people in this particular area are more, so there's a little bit of a gray area, right? Because if you know people in a particular area are more likely to spend on marriages, you might consider that a high risk activity.
So we are looking at consumer behavior. Okay.
Yeah. But in as much as that consumer behavior is segmented by ethnicity and community and that kind of stuff, you could also be opening yourself up to discriminating against certain communities. So dangerous.
Oh, so that is not the way to go ahead. You mean?
Yeah, I mean, besides, the government will come down on you if you do that as a bank.
Okay.
Or at least the government should come down on you if you do it as a bank.
But
I know our government doesn't always do it, but
Yeah.
Professor, from business point of view, it does seem like a rational.
no, it does seem like a rational thing, but it leads to discrimination.
Okay.
So I saw another example of that. For example, a lot of Muslim areas in Ahmedabad, because of the continuous Hindu-Muslim riots that kept happening over there, it was very hard for them to secure house loans. For the simple reason that banks were like not wanting to lend money because of the possibility that the house would get burned down in a fire or in an arson or something of that sort. As a result, a lot of Muslim house owners in Ahmedabad were discriminated against. Perfectly rational decision by a bank to say you are higher risk, because they were. But in any kind of fair society, you can't do that kind of thing. So usually there is government legislation against doing this kind of stuff. In the US, it happens a lot in black neighborhoods. You won't get those many loans and so on and so forth. But if you do that over here as a bank, the government will come after you with a very big stick.
Yeah, you can come off as insensitive. Yeah.
No, it's not just come across as insensitive. You will get huge fines. Huge fines. Like millions of dollars of fines. So it's not a good business idea either. Okay, so then there's another one, which is people who are having devices of brands like Samsung and Apple have comparatively low risk. Yeah, that may be a good one. If you have that much, additional income to pay for the Samsung or Apple premium, then yeah, you maybe you have enough money to pay back your loan really easily. Good point. Okay, so I think these are all some really good points that have come up over here. Let's switch back to the notebook. Okay. So do you want to take off from here, this point?
Yes. So basically we are dividing the T1 train that the data frame which has both target variable and features into X train and Y train here to give it to the model. So we have X train, Y train, X test, Y test. We have divided the data frames. Now, if you look at the X train, we don't have the risk flag column here. So dealing with categorical and completing features. So now we are dealing with the object type of columns.
Okay, so should I head back to the slides now?
Yes,
Perhaps?
yes.
Good point, I think maybe. The slides will enable me to sort of like summarize as well what we've talked about in the last half an hour or so. So here were some of the observations, like, age was kind of better, income was better, bureau score was better, house years was better. It was a favorable trend for car ownership, favorable trend for marriage. But there was some kind of abnormalities. 150 years old person showing up over here. Clearly, that was a data coding error. That when you actually maybe do this as a real world problem, you may want to get rid of these people out here is extremely low risk, high age people who are kind of funny out here. So, by the way, one of the problems by using a canned system such as SweetWiz rather than doing your own stuff to do this is what's wrong in this graph? What's bad about this graph?
Do you mean the left bar?
Yeah, the whole graph. Yeah, the left bar and.
In fact, that is the exact reason why I had raised my hand a while ago, because I
Oh,
wanted to
okay.
ask, what is this blue bar about?
This blue bar is the number of people.
Okay,
The fraction of your sample, if you like, in that particular bin.
All right.
So now that you've said that, what's bad about this bin?
Some kind of outliers.
Yeah, I agree. There's some kind of outliers out here, maybe like one each. So what has the outlier forced to happen?
I think the population is concentrated only between 20 to 30 years of age.
Exactly. And so if we wanted to look at the distribution, we would want to actually deep dive into this area, right? But because we have an outlier which is so far out, it is forcing us not to look into the exact distribution out here. You just put everything into one bin. How could you fix this? When you want to bring very disparate scales of numbers together, what transformation can you make? What scale can you put things on?
Can we do standard scalar?
No, that won't change a thing, right? For those who don't know, standard scalar is basically subtracting the mean and dividing by the standard deviation. This guy will still be as far as an outlier if you do that.
So should we remove the outlier?
We could, but even if you wanted to see the distribution without removing the outlier, what could we do?
Z score, like.
Pardon me?
Z score. Z.
Okay, you could do a Z score, sure, but you still haven't done anything which brings these scales together.
Yes.
Okay, so suppose I told you these are the numbers I have: 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5, 10 to the 6, 10 to the 7. These are very, very different, right? 10 to the 2 is 100, 10 to the 7 is 10 million. How can I bring these together on one scale?
Normalization between 0 and 1.
Okay, so you want to normalize between 0 and 1. But you are still going to have the same distance, right? Apart. You're going to have the same problem.
Log scale can be used?
Yes, log scale can be used, right? So you take 10 to the 2, 10 to the 3, 10 to the 4, up to 10 to the 7, that becomes 2 to 7. So when you do a log scale, what it typically tends to do, it brings in the stuff from the outside, inside, and from the inside, outside. So it will expand out the scale for you. And so often in these scenarios, you may want to re-ask SweetWiz or by yourself. If you look at this graph like this, make a log plot and see what it looks like. Okay, moving on. So these are high granularity categories, right? This is, I think, one of the points over here. And Sindhu was making this point with respect to the cities, right? There's a lot of categories here. So 1, 2, 3, 4, I don't know, about 20 over here, 20 over here. The cities, there might have been 50, 60 types of categories over there, right? So how are we going to deal with the situation? So somebody earlier said one-hot encoding, right? But take our cities, right? If I look at our cities and say, let's go here, and I put in a cell over here which says x underscore train 0 dot, what is it, city dot unique. I've got all these unique cities. You can make a list of that. You got a list of that. And I can take the length of this list, right? Whoa, too far up. I can take the length of this list. $316. So if I consider these cities as categories, I will have 316 categories. Now, somebody said we can deal with categorical variables by doing one-hot encoding. But look at this. We had how many features? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Suddenly increases from 13 to 13 plus 316, 329. Lots of features are always dangerous because in a high dimensional space, things get very far apart and machine learning models have a hard time. So you don't want to do that. So one-hot encoding is a good idea. By the way, for those who don't know what one-hot encoding is, it's just saying if I have 2 features or 3 features, encode them in 3 columns. So say I had a feature which was red, blue, green. Then I'll create a red column, a blue column, and a green column. And then I would have 1, 0, 0 for red, 0, 1, 0 for blue, and 0, 0, 1 for green. And then depending upon how each and every of my samples, like each and every row was red, blue, or green, I would have this 1 and 0 in there. And essentially that acts as an additional intercept for example, if you're making a linear model out of it. So the problem here is that if I have 315 things, that's just too many. Okay. So there are multiple ways to kind of like deal with this thing. There's a heuristic way which you can use, which is based on kind of like a prior knowledge. There's a way of combining stuff sometimes that you can do as well. But what you can do is do some rather simple ideas. So one very simple idea is simple label encoding. It only works with tree-based models, and we'll come to what a tree-based model is in a little bit. But a tree-based model, essentially, what you're saying is that if I have 315 features, give them the numbers 1 to 315. Just give them the numbers. So Warangal will be 5, and the next one after Warangal will be 6. Now, does not mean that Warangal is less than the next city, but you just encoded it in that particular fashion. That's this idea behind label encoding for these kind of high granular things. One-hot encoding is only use it if you have 3 or 4 categories, not more. And I won't go into vectorizers and kind of like, you can use a combination, of course. For low granularity, do one-hot. And for high granularity, you can do either vectorizers or label encodings or stuff like that. And these vectorizers come in various shapes. It's out of the scope to kind of like go into the vectorization, but it's actually the basis for a lot of, the kind of machine learning that people do today. And goes under another name, which is also called embeddings, basically. But you're taking your categorical space of 315 things and somehow the other mapping it to a vector. Okay. So here's an example label encoding. Like married has become 0 and 1. House ownership, there were 3 categories. Remember, there was renting, there was house owning, and there was neither rent nor house owning. So that became 0, 1, and 2. Car ownership was 0 and 1. Cities, we go all the way from 1 to 315. States, there are like what, 25, 26 states. How many states in India, by the way, now?
I think 29.
Whoa.
Not sure.
29.
Whoa. When I was a kid, there were 22 states. And lots of union territories. But I think a lot of that has changed.
Yeah. Not many bifurcations have happened.
Yeah. So, so just give them numbers. And that's what label encoding is. That's all it is. And we'll see why that may work. It's a little bit of a wrong idea, to be very honest with you, in the sense that if you put Maharashtra as 1 and Gujarat as 2, does not mean that Gujarat is greater than Maharashtra. But it's one way to do things. And one-hot encoding is this idea I was telling you earlier, that you do these kind of zeros, right? So here, if you want to do the various professions, you just give zeros in all of these kind of things where you are not one of those. I should have actually put an example of having a 1 somewhere in the slide, but you can imagine that maybe this person is a chartered accountant. There's a 1 in this chartered accountant column for him. Okay, that's categorical features. How about numerical features, right? For each variable, you might have some missing features. This often happens because data was not coded or coded. So you can do some kind of hard-coded missing things. A lot of time you'll see minus 99, minus 9999. Often when you cannot have a negative value, you do that. Often people will do an imputation of that column. If something is missing, they will take the mean of everything in that column or the median of everything in the column and put it in there. In some algorithms like XGBoost, you can just have missing values as a separate thing, and it'll deal with it. Similarly, you might ask, what should I do with outliers, right? I can cap outliers. I can say if my value is 150 years, okay, I'll put you in the 100-year bucket because you're not 150 years. Anything more than 100 years is like the 100 years bucket, or if you like the really old bucket, so to speak. I can drop those values, just get rid of those rows where the outliers are. Or I can just directly use it in a tree-based model. This is one of the advantages of tree-based models, that you can directly use this kind of stuff. Okay, so now I've been talking about these tree-based models. So I should actually go a little bit into tree-based models. I'll do that in a little bit. So if I have these kind of NANs, I can just impute. So here, for example, you just put the average age of 26 in there. Okay, we did this test train split. You can randomly split. You can do a stratification split. Always process your features after a train test split. Do the EDA after a train test split. Otherwise, you will get this leakage problem. Okay, so getting back to the code for a second over here. Sindhu, do you want to go ahead with the label encoding?
Yes. So as we saw, we are going to go with ordinal encoder. That means we are, as professor said, we are going to give numbers to the cities and states. Doesn't mean anything like it doesn't mean Andhra Pradesh is greater than Telangana or whatever. It is just a number, but to classify this this data has come from different state. So if you go to so what we are using here is ordinal encoder.
And ordinal just means one number after the other. That's all it means.
Yeah, it gives 0, 1, 2, 3 like that. As you can see, city it gives 94 to 19, 131. These numbers, each number will belong to some city. Like 94 could belong to Warangal, 219 could belong to Ahmedabad. So it's like that. And ordinal encoder we are using here from sklearn pre-processing library. And what we are doing is fit transform. What fit does is that it will allocate each, like it will pick each column from string call name list that we are giving here. So one of it is city. So in city, it will go and see how many cities are there, and it will provide each number to each city, and then it will transform all the data according to that city name, state name, house ownership, so profession, all these things it will transform. So we are doing fit transform. For test data we are doing transform because we want to follow the same numbers that we have given in train. We want to follow the same notation there of an ordinal encoder. So we are only doing transform on test set. Yes. So as we go down, we see that the shape of the train set. Okay, we have 7 of the categorical variables ordinal encoded now. Now all the data types you can see, they were object string types. Now it is all integer. because we have ordinal encoded them. Um, so what are the categories that we have encoded are these. One of the profession category, you can see there are professions. It has encoded married and single. It has encoded array of how rent ownership. So all these things you can say zero. It gave for air traffic controller. One was for analyst. Two was for architect. Three is for army officer. Like that, it has divided it. So it is giving from this call, like how it has divided the data. What are the categories that we have divided into? So these are all the cities, and then concatenating numeric and categorical. So we want to now add the new data that we have produced here, like pre-processed data, and so we are going to concatenate the categorical variable data, ordinal encoded data we have in train str, and the numeric data that we have in train 0, x train 0. That's what we are doing with pd.concatenate, and axis one means that add the column beside it, not under it. Uh, so that's what we are doing with both train and test columns. Uh, so we have produced a new data frame which has a pre-processed ordinal encoded categorical variables and numerical variables. So you can look at it, the whole data frame now, training data frame. Now we have the ordinal encoded data here, and then we have numerical categories, numerical columns here. So we have both the data here. So I think we need to go back to the presentation.
I think we can probably just finish this label encoding part, right? For the Ys.
Yes, even Ys we have label encoded. Label encoding means 0 and 1, right? So here we have like risk as 0 and 1. So we have done that. So both of them, for train and test, we have fit transform for train and transform for test.
Because you're getting all the information about the labels from the training set. That's why there's a fit transform.
Yes.
And for the test set, there is just a transform, because once you've got the labels, you can use them. Now it's kind of, you might find this a little bit weird, right? That once I do that, I still get 0 and 1. But that's because when you just have 0 and 1 as your labels already to start with, it's not going to change anything. It's just going to give you back 0 and 1. But on the other hand, if you had 3 labels, right, A, B, and C, then it'll label encode these as 0, 1, and 2, for example. And that's why you always want to label encode the Y, just as a good practice. You didn't need to do it here. You could just directly use the Y train directly. But it's just good practice to do it, because it generalizes to the situation where you have more than 2 labels. Like the MNIST data set I was talking about. Okay.
Yeah. So basically our model, it doesn't take any object. So even if we had some object like yes, it is risky, or no, yes or no, then it would have turned it into 0 ones.
Yeah. Okay, so this is probably a good time to go back to the slides over here. So now we're going to build a model, and there are different kinds of models that are actually there. There's models like logistic regression, random forest trees, XG boost trees, SVM, and so on and so forth. And they generally, I would say, perhaps one way to think about it is that they fall into one or two different kind of categories. And the categories they fall into and are this kind. Can you see the hello on the screen?
Yes.
Yeah?
Yeah.
Okay. So suppose I have 2 features. Feature 1 and feature 2. And now I have some data. Then I have some more data. And I want to separate this data in some fashion. So one thing you could do is you could possibly draw a line like this. You try and separate the data. You're going to get some misclassifications. You see the reds that went on that side. Another thing I could do is I could perhaps maybe actually try and do a surface. Which is like that. All models which use these kind of lines and surfaces are typically linear models, or maybe even nonlinear models like neural networks, which are learning a surface. Now you might say, well, why don't I do this surface? What would be the problem with a surface like this?
Overfitting.
Overfitting, exactly. Because the more complicated, the more curvy I made the surface. That was like, I would have not got extremely high sensitivity to what's going on, right? So if I moved just one of these across, like if I took this red one and I just moved him across from here to here, things would go wrong very fast. So yeah, you want to have simple divisions. So that's one way to do it. There's another way to do this, to solve this problem. And the other way to solve this problem, so let's just go back and remove all these divisions. So another way to solve this problem, which we could come up with, is to do what trees do. And what trees do is that they will go in these two different axes and they will divide the space up. So they first might divide the space up like this. Now, let me actually go back a little bit further because, yeah. So they first might divide the space up like this. Now, I think you'll agree with me, there are no red to the right, no reds over here, only blues, but there's a combination over here. So then I could make the next cut in this data, I could do something like this. And I'm only allowed in this situation cuts which are axis parallel. So here is feature one. I'm going to cut feature one into two parts. This is how I construct a tree. This is why it's called a tree. So my first cut is going to be on feature one. So this will be like feature one. Let's call this value 5. So feature one greater than 5, feature one less than equal to 5. That's going to be my cut. My next cut, let's call this feature 2 value 3. I will make a cut if I'm less than 5. Feature 2 less than 3. Feature 2 greater or equal to 3. Something like this. Okay, no more cuts are required over here. Okay, so now I've done pretty darn good. I've got everything like so. And then I say, okay, I'll make another cut like this. So this is for feature 1 greater than 3. I'm going to cut it. Feature 1, let's say less than 4. Feature 1 greater or equal to 4. Okay, now I can go further and say, okay, let us decide where my blue thing is. Give me a second. I'll say that the blue thing is here just for the sake of argument, okay? Not a little bit on the left. So now I'll say, okay, let me make another division. Oh, I do not want to use that color. Let's go back to the gray color. Make another division like this. Then I'll make another division like this. And then I'll make another division like this. And by the time I've done, with these divisions, I can tell you exactly where the blues are and exactly where the reds are. This is a tree-based model. It's called a decision tree. Do you think this shares the same problem like that very curvy orange surface I drew? It's isolating each and every individual point, right? Eventually. You don't want to do that because make a small change in the location of the features and things change. So You'll learn this, by the way, in future workshops. The next workshop is actually all about overfitting. So don't worry if you don't entirely understand. But the idea is that you want your predictions to be somewhat robust. So this anyway is a decision tree. Decision trees by themselves tend to be extremely overfit because they zero in on very, very specific things in the data. So you usually combine decision trees. You combine decision trees in two different ways. One is just by adding a whole bunch of decision trees together. This is called a random forest. Other is to take the output, the classifications of one decision tree and then correct it by putting another decision tree and then another decision tree and another decision tree. This is called boosting. And boosting turns out to be one of the most successful algorithms ever for data which is in the shape of these kind of pandas data frames. And there's a particular variety of boosting called XGBoost, which has a lot of little tricks on it, which is extremely good for this. And so almost everybody will tell you that after you do some kind of baseline simple model, always try an XGBoost model because XGBoost models tend to work extremely well. Okay. So that's what we're going to do over here. We are going to do an XGBoost, here an XGB trees model, and actually run this. So let's go over and build this model. So this is the call in scikit-learn style for XGBoost. Now you'll notice that there's a lot of arguments that XGBoost has over here. I'm not going to go in these arguments right now because you'll learn more about boosting when you do the trees and ensembles workshop at the end of the sequence. But what I want to point out is that there are these various parameters that these algorithms have, like number of estimators, which is actually the number of trees you want to add here. Max depth, which is, if you remember the tree I was showing you there, you don't want to go more than a depth of 5 in this tree. That'll make sure you don't go into those two small little things going around each and every data point. Subsample is how you sample different features. Class weights is what weights the classes should have. Scale pause weight is what weights the gradients should have. Call sample by tree, I don't even remember what that is off the top of my head, but it's just another thing. So these numbers are all knobs. They're all things that you can tune. They're called hyperparameters. Next, in the next workshop on overfitting, you'll learn how to tune these hyperparameters on something called a validation set, which we haven't talked about earlier as yet. But right now, all we're going to do is we're just going to choose some values for this and not worry about this tuning that we have to do. The tuning is really important, don't get me wrong. But right now, we don't want to talk about it because we just want to go into how one of these models does a classification. So I just create this XGB classifier. And then in typical scikit-learn style, which we learned last time when we did regression, I put the X over here and I put the Y over there and I fit it. And boom, that's a fit with it. So let's run that piece of code to import all these things. And this will take a bit of time to run because it's actually fitting 300 trees and adding them together in some particular fashion. Okay, so while it runs, let me go back to the presentation. And talk a little bit about the next part of this. So
Professor,
we're going to have this model.
has a question.
Yeah, just 1 second. So we're going to have this model. That model is going to fit. How are we going to evaluate the model? That's the next part. Okay, question.
Professor, you just mentioned that to address overfitting, we do boosting, which is combining more and more of.
No, I didn't say to address overfitting, we need to use boosting.
I'm sorry.
I said we need to combine trees, but you can have a very nicely overfit boosting model too. But the combination of trees does address overfitting. Yes.
So how do we know what number of trees to be combined?
This is the hyperparameter stuff that I was talking about, and I'm not going to tell you today.
Okay, fine.
Just in the interest of splitting things up, right? I'm not going to tell you today how to do it, but the bottom line is that these numbers you see over here, these are probably not the best numbers to avoid overfitting. We're going to have to figure out how to set these numbers. Yeah. Okay. So now that this model has trained, let's step in and try and measure what's going on. Okay. So the first thing you want to do in any machine learning model is to make a prediction. So here I'm going to make a prediction as to what these things are going to be. So I make a prediction and I look at the actuals too. So if I look at these predictions over here, You'll see it's just a bunch of ones and zeros. High risk, low risk, high risk, low risk, high risk, low risk. How is it deciding which ones to put high risk and low risk? It's doing these probabilities. And I can get the probabilities by using a function on the XGBoost classifier called predict_proba, which gives you the prediction probabilities. Okay. And it gives them to you in a shape of like the probability of class 0 and the probability of class 1. So I just looked at the probabilities of class 1 over here. And if I look at it, you'll see I have a bunch of probabilities. So you see, for example, the first one is 63%. That's why it made it a 1. The next one is 51%. That's why it made it a 1. This one was 35%. So it made it a 0. So you see what it's doing. It's doing this, what I was talking about earlier when we were talking about the rain. It's using this 50% threshold, 0.5 probability threshold. Anything greater than 0.5 is going to be a 1. Anything less than 0.5 is not going to be a 1. Now, I think we discussed that this is the choice of this threshold is also an important thing. And what this function does over here is, which one am I talking about? I'm talking about this one, predictions test. Is that it gives us ones and zeros based on this 0.5. Now, with the caveat that this is not necessarily the best possible choice, and we will talk about that in a much later workshop, let's go with what it did, which is to choose these 50% probabilities. When it chooses these 50% probabilities, now you can actually calculate various things out of here. And these are the various metrics you might want to associate. Now, these metrics, I think you will agree with me, will change if I choose a different threshold. If I choose a threshold of 60%, in fact, let's talk about something ridiculous. Let's choose a threshold of 100%. If I say you need to have a probability of 100% to be classified as high risk, then nobody will be classified as high risk. Because people may at most have 99% chance of being classified as high risk. So at 100%, nobody will be classified. And if I say it is 0%, then everybody will be classified as high risk. Both of which are not very useful models. Right? So the threshold is somewhere in between. It may not be a 0.5, but it is somewhere in between over there. Here, the default thing that XGBoost does is to give us 50% threshold. Now, you can compute various things with this 50% threshold. Okay, so what can I compute? I can compute what's called a confusion matrix. I'll give a nice display for it over here that you can get from scikit-learn. And what the display is saying that, look, these were the true labels. 57,144, you remember these numbers probably in 2,309. These were low-risk people. These were high-risk people. Here are my classifications. Here are my predictions. Okay, so I predicted so many people to be high risk and so many people to be low risk. Now, I got 11,985 predictions absolutely correct amongst the people who were high risk. These were people who were high risk, and I predicted them correctly to be high risk. I got 57,144 predictions right amongst people who were low risk, and I predicted to be low risk, 0. But I got 20,000 predictions wrong. These were people who were predicted to be high risk, but were low risk. These are called false positives. And they're called false positives because they're actually negatives. They're zeros. They're not high risk, but I predicted they were high risks. And they got 2,309 of these wrong the other way, in the sense that they were high risk people, and I predicted them to be not high risk people. Now, as a business, I have to ask the question, which of these two types of errors am I more willing to sustain? If I get 2,309 people over here who were high risk, but I was not able to predict them correctly, This is 2,309 people on which I might lose my loan. Could the loans on 2,309 people create an existential crisis for me as a business? Maybe, maybe not. But this is the number I can calculate, what the size of those loans are, how much of a loss am I going to take because I made this mistake. On the other hand, over here, I made this kind of mistake. These were people who were not high risk, but I predicted to be high risk, and I didn't give them loans. So I have 20,000 people who another bank will go and possibly give loans to. So I've lost a lot of customers. So now I have to think about this optimization. What is the lifetime value of these customers I could have had versus the people I'm going to lose money on? So I think you can realize this is a complicated calculation. It needs to be made with your chartered accountants or your business people and all of these kind of things who know what's actually going on with your loans and so on and so forth. It's not something that you by yourself as a machine learning person can do. You need to bring in the domain knowledge at this point to make these decisions. But the thing I want you to understand is that these numbers change with the threshold. Think about it. If I said I want an 80% threshold, 0.8, anything above 0.8, I will say is fraudulent. Not fraudulent, is high risk, and anything less than 0.8 is low risk. Have I reduced my number of high risk people by doing this? The number of people who I predict to be high risk? Anyone?
Yes, reduced.
I have, right?
Yes.
So I'm going to lump sum, take a whole bunch of numbers from this right side column and put them into the left side column by doing this. As a result, I'm going to reduce not only the true positives over here, the people who were high risk and who I correctly predicted as high risk, but I'm also going to reduce these guys. Should I do that? Well, the answer is you tell me what the cost associated with it is, and I'll tell you whether I should do that or not. So do you now understand that this is a possible way of trying to figure out what this threshold is to look at the costs, balance it, and make a business decision on which one it is. So in the real world, you always have to think about these kind of things. They're not directly germane to the modeling you did, but they come in from the business side. Think about the cancer situation I was telling you about earlier, right? If I'm making a cancer prediction and I have lots of false negatives, what's a false negative? Person who doesn't have cancer, person who has cancer, but I predicted does not have cancer. That's a freaking disaster. I'm killing people. I don't want false negatives. I want to move as much from this side to this side. If that means I'm making 1,000 additional people go get biopsies, okay. But I'm not killing anybody. So in that case, my threshold, I won't set to 0.8. I'll set it to be extremely low, 0.05 or something. Intuitively, you knew that. You have a 5% chance of cancer, you go to the doctor, get a biopsy or something. But this way, you can put it in the language of cost. Right? Associate a huge cost with making the mistake of killing people. $1 million for killing people. $1 for making a person take a biopsy. So when you have these kind of lopsided costs, then the threshold changes. Now, how exactly you do this? There's a lot to learn. Clearly, I cannot tell this to you in one workshop, but I want to give you a feel for how you make these kind of choices. And these choices can be seen on something called an ROC curve or a precision recall curve. So with this 50% threshold, I can do a classification report, which gives me a bunch of numbers, like an F1 score, which kind of tries to mix together this true positive stuff and the false positive stuff. So if you have a F1 score, which is closer to 1, you're generally doing kind of well. So you can see over here that I have a good F1 score on the negatives, as you might expect, right? Because most people are negative, and not so good on this. And it's an overall kind of average one of 0.67, which is not a terribly good F1 score, but not terribly bad either. It's not a bad model per se. At the 50% threshold. Now, if I wanted to see how this model changed as I changed the threshold, I do something called an ROC curve. And an ROC curve essentially changes these probability thresholds and sees how the model is doing. It looks like this. And the AUC is the area under the curve, which is like 86%. If you look at this whole box, it's really a square, and its area is 1. So this is saying 86% of the area is below this orange curve, which kind of makes sense because already 50% is here. And there's an additional 36% here and about 14% left over there. The higher the AUC, the better off you are. The closer to 1, the better off you are. But this diagram actually shows you very interestingly what you want to see in terms of these false positive rates and true positive rates. So look at the bottom left of this diagram. On the bottom left of this diagram, you have a false positive rate of 0. As you go to the right of the diagram, you have a false positive rate of 1. Everything is false over here. So if you think about it now, how do you get everything to be false in your prediction? What do you put your threshold at?
0.
Because
0, exactly. And if you want to get everything to be true,
100.
Oh, sorry, it's the other way, right? If you think you want everything to be the positive class, the true positive, you get 100. Yeah. So this curve is basically the curve you get as you change these probability thresholds. And so now you can pick. So if you think about it, these are actually different models at these different thresholds. And you can pick each and any one, based upon these costs, you can pick each and any one of these models. But the overall performance of this thing can be told to you by this entire curve. Similarly, you can do a precision recall curve. And that looks like this. And I won't go into a great amount of detail in the interest of time into precision and recall, but I think you can go read up on precision and recall and where you want to be on this curve. But it's again the same idea that you have all these thresholds and you are going at different precisions and recall. So this is precision on the, I should have put a label out here. plt.x label, precision, plt.y label, T label? Oh, sorry for that. T is next to Y on the keyboard, which is why it's coming like this. Okay, let me go to the slides to elaborate on this a little bit. Just so like summarize what we've talked about. Remember false positive, right? We are rejecting customers. We talked about this. We're saying, hey, we're over predicting risk. And so we're rejecting customers, which we should not be. False negative is where we are accepting customers when we should be rejecting. And as I said, the balance between those two depends upon what the relative costs of these two things are. Now, the true positive rate is, you get the idea. It's kind of like these true positives divided by the true positives plus false negatives. False positive rate is false positives divided by false positives plus true negatives. So it's the fraction of the upper thing here and the fraction of the lower thing out here. Here are what precision and recall are. Look at precision first. Precision is true positives divided by true positives plus false positives. So it goes vertically on this confusion. This thing is called a confusion matrix. And recall is true positive divided by true positive plus false negative, which is the true positive rate. It's the same thing. These two, this is the same. This upper thing over here is the same as this thing over here. Okay. So the F1 score that I talked about is the geometric mean of this precision and recall with a number 2 thrown in for good measure. And the higher it is, the better off you are, because it is kind of balancing these two. Once again, I warn you that you may not want to balance precision and recall in exactly the same fashion. But in general, this is a rough idea of how good you are. Why might you not want to balance them in exactly the same fashion? Think about it, right? Precision is true positives divided by true positives plus false positives. You want this number to go down. You want the false positives to go down from a business case, right? So you want to be sending this precision as close to 1 because you want to send FP close to 0. So in other words, on this curve, you want to go to a precision of 1. You want to go in this direction. But look at recall. Recall is true positives divided by true positives plus false negatives. It's talking about this bottom row over here. Okay. Over here, you're trying to change the false negatives to come to 0. And so you are trying to go up there. Now, which one of these is more important is the question you need to ask, right? So you might make the statement that it is more important for me to minimize the false positives because I want to retain all these customers. I don't want to reject customers. I want to retain all these customers. Than it is to be, to be accepting customers who are likely to default, because that's how my cost benefit analysis worked out. So then I want to go more in the direction of having a higher what? Precision, right? At the cost of a lower recall. So I might be wanting to be more around here. I don't want the recall to go all the way down, but I might want to be somewhere over here. So this is how you would pick the model. What is more important to you? What is the relative importance of these things? Okay. And that will land up picking a particular probability threshold for you to choose. Does that make sense? Even if not in the exact technology, but the idea behind it should make some sense to you. Okay. So these are the performance metrics that you want to look at. And I put these here into 2 functions. So you can just use these functions to create a little report for yourself. And get these numbers out and so on and so forth. But also in the cells above, you can see how to do them individually. There's a lot more to learn on these ROC curves and precision recall curves. But if you take a proper machine learning course, you will be doing that. Okay. Now, this is the performance. And you have seen the performance depends upon the threshold of probability you choose and upon what you want to emphasize. You want to emphasize the true positive rate, the false positive rate. You want to emphasize precision, or you want to emphasize recall. Right? And these things are different. Now, having done all of this, you still don't know how this model has worked, what it has found to be the most important thing. And there are many ways to do this. There's a library called LIME. There's the library over here that we're talking about called SHAP, which uses game theory to do this. LIME learns local linear models, basically. There's something called permutation importance you can do for tree-based models. Actually, permutation importance you can do for any models. There's a Gini coefficient-based feature importance that you can do for tree-based models. But in all of those, you're trying to ask the question, which feature mattered most? And you're trying to ask that question in 2 different ways. Over here, I'm only going to show you one way, which is globally, which feature mattered most. But you can ask this question of very individual data points too. For this data point, what mattered? Why was this person rejected? Why is this an important question? Because you may require it for compliance. Typically in financial scenarios and in medical scenarios, compliance is actually quite important. If you are not giving a person a loan, if you're rejecting a person for a loan, you might be asked by the government to say, what are the reasons you do this? So this interpretation part becomes really, really important in these scenarios. Over here, you're going to import SHAP. Here's my training data set. And I'm going to run this piece of code. It's just a little piece of function. It takes the model and creates a tree explainer out of it. And the SHAP values, get us the SHAP values over here. This is going to take a little bit of time to run because it's actually doing some fairly complex calculations and looking at various different local models that it actually runs. But it'll give a result that looks like this at the end. And the result is telling you that globally, over averaged over all the samples in the training set, which were the most important features. And you can see clearly income is important. Credit score is important. City actually turns out to be fairly important. It turns out to be next in this list. Profession is important. State is important. Experience, device, okay, that's kind of all the same. Surprisingly, as you might have thought, that age and the other things that were kind of dependent upon age, like current job years, current house years, are not that important. Married is not that important. This came as a bit of a surprise to me. My suspicion is that house ownership is not that important because in India, there's not that much house ownership. There's a lot of rental or you're staying with your parents. So that's why this is probably not that important. Car ownership, I think it's becoming more important now, but not everybody has cars, right? So I can see that but the marriage part was a bit surprising to me. It may not be important in the Indian context, of course, because before marriage, you're typically staying with your parents. You're not trying to find your own house with your wife or husband or whatever, right? So I'm not entirely sure I understand some of these things, but this one is kind of obvious, the income and the bureau score. I'm a bit surprised, actually, that age came that far down. Given that the older you are, the more likely you are to have gotten to some kind of like a stable situation in your life. So these are the kind of things you may actually want to sort of like understand as to why it's happening. Now, this is a global thing, a global measure, but you can make individual measures as well and try and see for any one person, what were the things that made the choice? In other words, you can kind of go down for any one given person. You can kind of go down, if you like, one of these trees and see what happened for that person. So this is why tree-based models are actually quite useful as compared to a lot of other models. It's not like drawing some kind of geometric boundary. It's these various choices on cuts on features that it's going to make, and which is important for explanation. So this is why it's the other reason why people like tree-based models a lot. Okay. So the rest of this is kind of homework, where we're asking you to do like one-hot encoding and all of these other kind of things that we talked about. And I think we're actually done for the most part. Let's talk a little bit about model selection, and I think then we're kind of done. So we are going to compare these areas of different models. Randomly speaking, you'll have 50%. The AUC roughly is the probability that the model ranks bad over the good, so to speak. So we can either choose by having a higher AUC between different models. All things aside, you should choose a high AUC between models, but that is not telling you what threshold to choose. So that's the second decision you need to make. Again, you could use your precision recall curve to choose it. It's a single value to measure this kind of like greater than positive kind of rate that you have. Okay, so my point over there is that there are two things that you need to think about. I'm comparing different models. One might be a gradient boosting model, which had, bear with me for a second as I go back, these arguments in there. As I change these arguments, the AUC is going to change. The AUC PR is going to change. The area under the precision recall curve is going to change. So I can formulate my decision-making process as a two-step one. I can choose the best model by looking at the one which has the highest AUC, because that's the one that is most likely to be good over an entire variety of thresholds. I.e., if your modeling assumptions changed, if your retention cost of a customer changed, you could still probably do well with one of these models. So you notice there is this tension. The tension over here is between choosing the best possible model you can, knowing all the business assumptions that you can make, versus getting a model that is somewhat robust to changes in these business assumptions. So when you want to get a model which is somewhat robust to changes in the business assumptions, you look at these areas under the curves. You look at the area under these curves and see which model gives you a higher area under the curve. And then once you do that, put in the business assumptions and you can choose your thresholds and do stuff like that. So do you understand the prescription here? Choose a model that's best on the average because your business assumptions are somewhat uncertain. You don't know all of these kind of things. They all involve projections. And then choose the threshold based on that. Now, some of you might say, oh, but what if I knew that my business assumptions were in this range? And I'd be like, go for it, dude. If you know that your business assumptions are in that range, just take the area under that and compare models based on that. Now, if this sounds a little bit complex to you and not completely prescriptive, it is. You can't check your brain at the door. You have to use your brain. You have to use your business, your domain knowledge to do things. But the simple way that you can come up with a reasonably good model is just to look at the entire area under the curve. So if you want to have like the one takeaway, or what should I go and do? Compare models by looking at the area under the curve. That will work over a variety of situations, a variety of thresholds, right? And you'll be in good shape. Okay, so going back to the slides here. Then after you do that, explain the model, try and understand how the model is working, what features is the model using a lot of, see if they make intuitive sense to you, okay? Think and see if these make sense. Are there features that are explaining too much of the variation? What would happen if you drop that variable? Check that. And there's lots more to be said about this. But, in the interest of time, I'm not going to go about it here. So here are some different models. This is with imputation, this is with one-hot encoding, and this is just a plain XGB. You look at the AUCs, they kind of change. Imputation is better. Plain, it's about the same as this. One-hot encoding, look what happened. It only got you 0.77 in this AUC and 0.41 in the AUCPR. And that's because it became too big a model and could not handle things properly. Okay. Finally, these metrics should be converted, as I said, to some kind of business-related cost function, right? False positives, they impact user retentions. If so, what is the cost? False negatives, what is the cost of the default? Is that a higher cost for you? Right? We had less false negatives. We have more false positives. So more false positives times the user retention cost. Less false negatives times the default cost, which is probably likely to be a bit higher. What's the thing? Now think about, once you do this, think about paying attention to the interventions that you need to do. Think about the probabilities, right? If the probability of risk is extremely high, it's above 0.9, you might say hard decline. I'm not going to. But if the probability is like 0.8 to 0.9, you might say, okay, let me decline, but let me find the reasons for it and keep track of those reasons. That's the explainability part. Because those reasons might change. That understanding might change. So you pilot a model like this. You deploy the model. You listen to the users of your model, you bring in all these stakeholders, and that's how you do it. And then when assumptions change, you don't necessarily have to revisit your model per se, but you may have to revisit these costs. If your features themselves start changing, if your age distribution of your customers increases, then you possibly have to retrain this model, right? Because this model worked under a particular age distribution. So this is called distributional shift. And then you retrain the model and go again. So this is the entire life cycle of one of these classification models in the real world. Okay. I think it's a good place for me to stop. I'll take any questions.
May I?
No, you can go ahead. Yeah.
Professor, I have a couple of I have a question about a couple of concepts that were mentioned. I may not be able to point exactly in what context they were, because it's a lot of new stuff that I'm listening to today.
It is a lot of new stuff.
Yeah. So the first is, there was I think Shruti mentioned log scale or log scale. So what is that?
So it's when you take the logs of numbers. So logarithms are a particular function.
Okay, so the one that we refer to in the 10th standard, log table.
Exactly. It's a log table from the 10th standard. That's precisely it.
So, like, do I need to revisit that concept, or is it?
Yes, you should revisit that concept. But a very simple way to think about it is powers of 10.
Okay.
So 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5, 10 to the 6. Log to the base 10 of 10 to the 2 is 2.
Okay.
So log is basically the power to which you're raising something.
Okay. And
so think of now 10 to the 2 is 100. 10 to the 7 is 10 million.
Okay.
Just put the zeros and you'll see.
Yeah. Okay.
Right?
And the other concept was you mentioned.
But it's map. If you take the logs, it's mapping them from 2 to 7.
2 to 7. What does that mean?
So 10 to the 2
becomes
2 when you take the log.
Okay. Yeah.
10 to the 7 becomes 7 when you take the log.
Okay.
The difference between 2 and 7 is 5.
Yes.
The difference between 10 to the 7 and 10 to the 2 is like 10 million minus 100.
Yes.
Which is huge.
Values are
log brings things down on a much smaller scale.
Oh, okay.
And that's why you can see outliers in a much more easy fashion.
All right. Another concept that you mentioned was, the word that you mentioned was permutation. So is it about the mathematical concept of permutation combination?
Yes. So there's one way to look at any model. And one way to look at any model is to make a permutation of the features in that thing. So let's take age. Okay. I have some machine learning model which is using all these features to predict whether somebody is going to be high risk or not. Let me just take the age column. Let me permute the column. So somebody who was 100 years of age, I call him now 5. Somebody who's 5 has become 70, and some 70 has become 25, and 25 has become 33. So I made this permutation. Now, if this feature was not important, is not giving anything to this model, then this permutation should have no impact on the predictions. So by finding how much of an impact that permutation has on the predictions, a change in the performance of the model, I can say how much impact this column had. And this is called permutation importance.
Yeah, okay, I got it.
It's a very general way. It's expensive because you have to retrain the entire model. But it's a very general way of quantifying how good a feature was.
But then I'll need to study the concept of permutation combination as well.
No, just think about permutation.
Yeah,
just
that's
change
the idea of permutation. Yeah.
Okay.
Thank you. It was an interesting lecture. Thank you.
Any other questions, folks?
Sir, I have a question.
Yeah.
Like the model that has given the result after training and predicting on the test set, then how come this ROC or the confusion matrix can change the model prediction value, like accuracy? So if I put the threshold 0.5, 0.6, so these
Yeah, no, go ahead.
So my question is how these confusion matrix or these are able to change the result of that model prediction.
So this do you agree with me that this confusion matrix will change if I change the threshold?
Yes, sir.
Okay, so if the confusion matrix changes as I change the threshold, the number of positives and the number of negatives have changed. So the accuracy will also change, right? As I change the threshold. The model has not changed. I've changed my decision-making process.
Yes, sir. Right, sir.
So when I change my decision-making process, what I am calling a positive and what I am calling a negative, or what I'm calling a 1 and what I'm calling a 0 has changed. This is the important part to understand. When I look at this particular piece of code over here, and that gives me a bunch of 1s and a bunch of 0s, that's a prediction with a 50% threshold. That's the default. For good reason, right? Because at a 50% threshold, you're more likely to be something than not. But as we have discussed, it may not be the right threshold for our business case. Or in the cancer case for our biopsy situation. I like the cancer case because it makes it very clear to you that you would not want to choose a 50% threshold.
Yes.
Right? So the model has not changed. The predictions of the model have, on the other hand, because what is important to you has actually changed.
Okay, sir. Means threshold value has to be put in while predicting on the test value.
Exactly.
Like,
and if I just go in directly into xgb.predict, that's taking a threshold of 0.5. And when you are doing this ROC curve that I was talking about, it's actually taking these different probabilities. So you'll see over here, it says that false positive rate, true positive rate, and probability thresholds at which you call something positive or negative, all three come out of this function. And look, as it takes as an input, it takes the y's and it actually takes the probabilities because it's going to mess around with the probabilities now.
so basically, ROC curve takes back to the prediction test and then again does the calculation, creates the confusion matrix, and draws the curve here. Basically,
in fact, it does not create one confusion matrix. It creates thousands of confusion matrices, which are along this. And then calculates the true positive rate and the false positive rate, and then it gives you a point on this graph. And I think you'll agree that confusion matrix is going to change with the threshold.
Yes. You got it.
Excellent.
And one more question, sir.
Yeah.
If the ROC you see shows the 86%, so can you explain like what is the term? What is the meaning of it in what is the term 0.86 for ROC UC? So can you?
So this AUC, right? We are talking about this 0.86. Yes. That is the area under the orange curve. So this area here.
Yes, sir.
That's what it is.
So how to interpret it in words that I want to say?
Yeah. So in words, basically, it's roughly telling you what's the probability of a negative compared to the probability of a positive. The higher the AUC is, so if I had 2 or 3 models to choose from, I would choose a model with a higher AUC because that model is going to look like this. It's going to look something like this. And why is that more interesting? Is over a wide range of assumptions, it will optimize the correct things for you. If you want to change the true positive rate to be higher for a given false positive rate, it's better if you're up here. So you see, fix the false positive rate. Say here. You want the true positive rate to be higher, you want to be up here. Fix the true positive rate. You want the false positive rate to be higher, be further up. So the more further you go, the better off you are. Without locking in the assumptions, right, of those various costs I was telling you about. The cost of a default versus the cost of of losing the customer, right? Because you said, I'm not going to give this guy a loan. False positive. Make sense?
Yes, sir.
Okay, if there are no further questions, let's thank Surojit and Sindhu for putting together a very nice workshop.
Thank you, team.
Sir,
Thanks, folks. And next week, I'll see you for hyperparameters, overfitting, and all of those kind of things.
I'll just walk them through the homework and the submissions.
That would be super. Let me stop sharing.
Yeah. Can you guys see the screen?
Yes, we can.
Yeah. So this is the repo for our today's workshop. It's the link for the same is also present in the chat. And now in this repo, there is the notebook that we use today. In that notebook, there is a section called homework, which you have to complete. And once you have completed the homework, there is a forum that we have where we usually ask people to post in questions and submit their homework. So this forum, discourse.univ.ai, the link for the same is also in the chat. I'll also put it in the Discord chat as well. This forum has a thread called questions on real world classification, where you will be able to ask questions and have any, like if you have any doubts or anything, you can post it over here. There's also another forum called homework discussion for real world classification, where there is a link for the homework submission form. You have to click on this link and fill the form after you have completed the homework. Only if you fill the form, you'll get a certificate. The certificate has some parameters. You must attempt the quiz and upload your homework solution notebook. And once that is in, we'll give you a certificate. The deadline for the home submission is till next Sunday. You can submit anytime before that. We also have a couple of workshops upcoming. So on this Thursday, the upcoming Thursday, there's a workshop on visualization for communication, which is also going to be instructed by Professor Rahul. You can register for the same over here. On the upcoming Saturday, we also have data science workshops. So we have 3 unsupervised learnings and overfitting and regularization. In this sequence, we have overfitting and regularization, which is again going to be taken by Professor Rahul. You can register for that over here. The basic concepts of machine learning is the link for that. And you can register for it over here.
It's
So
the
this
orange
is the
one.
registration link. Yeah, the orange one, the last one. And so if you have any questions, you can post it on the questions thread in the discourse, or if you prefer it, you can put it in the Discord thread as well. So thank you, everyone, and hope to see you in our future workshops also. If there are no more questions, thank you. And
I
have a
have
good
I
day.
have one doubt. Yeah,
Go ahead.
like yeah. So the code for Professor Rahul is O1, I guess, for selecting his workshop. Is that so? Because
Yes, I
I
believe
can,
so.
because I can see there are many code written O1, R1, C1.
Yeah, R is red, O
And
is orange. So yes.
okay,
Yeah.
Yeah.
okay, thanks.
Cool.
So thank you, everyone. If there are no more questions, have a good weekend and see you again soon.
Thanks, everybody.
Bye.
Bye.
Thank you.
thank you, sir.
Recording stop.